So model 1.2, still under the first module. Like I said, we just broke it down to very short videos for it to make more sense and for people to understand. So for this 1.2, we're going to look at mixtures. We'll follow this outline, the definition of mixtures, different types of mixtures, and we'll go to solutions, types of solutions, and some measurement of concentration of solutions, and then we'll look at ideal solutions, look at some illustrations, and we conclude. Mixtures. Mixtures are combinations of two or more substances in which each substance retains its own composition and properties. Now, elementary chemistry will remember what we talk about mixtures and compounds. And of course, mixtures can be separated following physical means. That's why we call them mixtures. And we say each component still retains its own composition and properties. And that's why there's no chemical reaction between the components. And that's why it's easy, for us to separate them by physical means. So I can have a mixture of salt and water, which of course I can evaporate the water and still have my salt back. You can also have a mixture of ethanol and water, which is the alcohol in our palm wine. That's why most of us who come from riverine area will find out that this is how they end up, evaporating or distilling off ethanol. Temperature of ethanol, the boiling temperature of ethanol is below the boiling temperature of water. The boiling temperature of ethanol is 78 degrees C. So it's easy for you to heat that mixture at 78. And around that temperature, only ethanol will boil. And as ethanol is distilling off, it is collected. And of course, at the end, we will have our ethanol, which they use, most of them, what you call kai. They use it in, manufacturing the kai. And that's why some of them who may not know the concentration of what they have produced, like sometime we had a news of what happened in one area like that, where people, after taking such, we call it illicit gene, after taking that, most of them died out of it. Because at that high concentration, it can cause corrosion, corroding the esophagus, corroding the stomach, the intestines, and of course, leading to very dangerous situations. Now, mixtures can be classified as either heterogeneous, and that is mixtures that are not uniform throughout, or homogeneous. And homogeneous mixtures are also called solutions, and they have uniform composition and properties throughout. Now, if you make a cup of tea, just your water and your milk, as long as it's not saturated, you turn it. After using your spoon, maybe turn it, you have produced a homogeneous mixture of your milk and water, which means if you drink from any side of that tea, you will have the same taste. But in terms of heterogeneous, like I said in class, it's easy for us to define this heterogeneous. Let's assume a student, students like taking this, like drinking gari. Now you have the raw gari like that, the last one you have, exams is about ending and you're about going home. So there's no money. Your little beverages are finished and you want to just manage yourself for another 24 hours before you leave. And you have your gari, you just have it in a plate. You want to go and bring water and somebody bumps into you and the gari, falls on the ground. Now there's every tendency that, assuming you don't have any other gari and you want to scoop that one, if you scoop that gari from the ground, there's most likely to be a mixture of gari and sand. So when you look at some sides of that mixture, you see more gari. When you look at one other side, you see more sand. That's an exactly perfect example of heterogeneous mixture. And you might decide to use your spoon and scoop off where you have more sand. And of course, this is a pure case that you can also still separate. If you soak both the gari and the sand in water, you find out that the sand will settle more down at the bottom of your container. So you can easily filter off or decant and get more of the gari with the water on another bowl. By so doing, you have separated your sand and gari. So what we're trying to say is that a heterogeneous mixture does not have uniform composition, while a homogeneous mixture has uniform composition. Of course, I've said this, mixtures can be separated by physical means because each component retains its properties. Now, important characteristics of mixtures is that their compositions can be varied, and also each component of the mixture retains its own properties. Now, solutions. Remember we said homogeneous mixtures are also called solutions. So we're looking at solutions. We also looked at solution in the previous module. Now we're looking at solution again in a different way. So a solution is regarded as a completely uniform mixture of two or more substances. So solutions are homogeneous. Remember that's what we said. Now the same properties such as density, refractive index, concentration, or even appearance in all parts of the solution are the same. So if you take a little, maybe like the cup of tea, just take a little syringe, collect some quantity of that tea from one side, call it sample A, collect from another side, call it sample B. If you check the refractive index, it will be the same. If you check the concentration, it will also be the same. Now, but at the molecular level, a solution cannot be perfectly homogeneous. Why we say this is because the terms solute and solvent are used in connection with solution. So we want to differentiate. When we have these components make up the solution, we must have one that is a solvent and the other will be a solid. And we said that the solute is dissolved by the solvent. So which means the solvent is a substance which is present in excess. And then the solute is the one that is not in excess. So we can differentiate two things, the solute and the solvent, which make up the homogeneous mixture, which we call solution. There are types of solutions, yes, different types. Gases in gases, gases in liquids, gases in solids, solids in liquids, solids in solids. There are so many types and different examples. But our interest will be liquids in liquids solution. And when we talk about liquid in liquid solution, there are three things that come up in terms of making the solution. There are some solutions that are mixable, that is, in all proportions, you mix them together and they will mix. Whereas there are some that are partially miscible, it's not possible that you have a complete mixture. Some will dissolve to some extent, while the other will not. We will say partially immiscible. And then, of course, we have totally immiscible. These things come to mind when we look at our polar and non-polar solvents. When we take like a polar solvent, water, and then we look at something like kerosene, you find out that if you bring your water, which is different, and kerosene, you cannot get a complete mixture. So we are interested in liquids in liquid solution, and that's what we'll discuss further. Liquids in liquids, solutions, we can measure the concentration. Of course, the concentration is about telling us the strength of that solution. For instance, if I want to say something about your class, I can ask, what is the number of students in this class? And somebody will tell me 200, 300. That gives us the strength of the class. But since we are looking at solutions that have solute and solvent, we can also decide to take the girls and the boys and call one solute, call the other one solvent. Let's assume the girls that are excess or more in number, we say they are the solvent and the boys the solute. Now it means I can decide I want to know the strength of the girls and the boys. So this is how we do that. In terms of solutions, one, we can use percentage composition. And this percentage composition, we can use weight by weight. I will say this is the number of solid contained in 100 grams of the solution. It can be volume per volume, and this is the volume of the solid present in 100 volumes of the solution. If you see this, we are saying volumes, which means it can be meter cubed, it can be cm cubed, it can be in liter. So whichever unit of volume we take must be uniform here. Now we can also have weight per volume, and this is number of grams of solid present in 100 dm cube of the solution. So these three can give us percentage, and each of these, once we multiply by 100, it gives us the percentage composition, weight per weight, volume per volume, or weight per volume. The next is gram per dm cube. This is the number of grams of solid per dm cube of solution. This is another way to measure concentration of solution. We also have moles per dm cube, and this is what we call molarity. This is, of course, what you normally use in your practicals, also with grams per dm cube. In your laboratory practicals doing titrations, you will be meeting molarity quite often with gram per dm cube. And molarity is defined as the number of moles of solute per dm cube of solution. Remember, we will still meet number of moles. Number of moles, which we use as small n, is equal to the weight of the substance in grams divided by the molar mass of that substance in gram per mole. So that gives us the number of moles. And we have another one. This is molarity and this is molality. You see the difference now. This is still number of moles of solid dissolved in 1,000 grams of solution. So we're no longer talking about still number of moles, but this one is per dm cube, and this one is dissolved in 1,000 grams. And we also have another one, normality, and this is number of equivalents per liter of solution. So sometimes you see all these labels on some solutions in the lab, some reagents in the lab, and that helps us to know the strength. If I have a clear liquid in a Ragolis can and it's not labeled, assuming it is even water, and I label it 1 molar solution of nitric acid, you see that anybody who sees that label will run away. But if it is acid and I did not label at all, and you look at it, you might think it's water. So that's why it's important for us to know the concentrations of solutions, and if we want to work with any of that, we'll be able to know the concentration of what we are working with. And of course, some of these concentrations can also be interchanged. There are others, like parts per million, parts per billion, milligrams per liter, and so on. There are so many, but at your stage, we just want to look at these basic ones that will help us to understand at this lower level what we are doing with solutions. Now, for solutions, we can differentiate two types again, which we'll take as ideal solutions and non-ideal solutions. And our interest is in ideal solution. I will say that this is a solution where no intermolecular forces of attraction exist. Now imagine, no molecular forces of attraction and repulsion. Is that possible? That's what you ask yourself. Now the word ideal again comes in, just like if you remember ideal gas, ideal behavior, ideal gas law, ideal equation. We look at ideal as this is what it should be, but in real sense, it is not that. So for us to approach the situation of ideal solution, the solution, one particular condition is that the solution must be very dilute. You know, when the solution is dilute, then it means you are most likely possibly not going to get an interaction between the solute and solvent because it's very dilute. You know, we can liken this to situation of exam in class. If you have 100 students writing exam and you have a big hall, you separate them far apart, then there won't be interaction. But if the class is small and you bring them together, then definitely they will interact. People will copy from each other. Now for ideal solutions, two things are important. One is vapor pressure of that solution. Now we're looking at two miscible liquids that form an ideal solution. Now for any ideal solution, the vapor pressure of its constituents is given by Raoult's law. And Raoult's law states that the vapor pressure of a constituent in an ideal solution is equal to the vapor pressure of that at that temperature multiplied by the mole fraction by which that constituent is present. Raoult's law acts to liquid solutions just like Dalton's law acts to, gaseous mixtures. So mathematically, we state Raoult's law as PA is equal to XA, P superscript 0. Now this tells us that this PA is the vapor pressure of that particular solution. Now XA is the mole fraction and PA superscript 0 is the pure vapor pressure of that component. Now the second important thing is the mole fraction. So we're looking at the mole fraction as the ratio of the number of moles of that particular component of the mixture divided by the total number of moles. Look at equation 2 is giving us that. XA, which is the mole fraction of A, okay, there's a mistake here. XA is equal to NA divided by NA plus NB. The second one is NB, where A and B are the constituents. And it's also good to mention here that generally or conventionally, we give a subscript to the solvent as 1 and the solute as 2. So if I say X1, then it means I'm talking about the mole fraction of the solvent. If I say X2, I'm talking about the mole fraction of the solid. But at any point you use any letter, maybe XA, XB, XY, X that, and you define what it is, we'll be able to understand whether you're talking about mole fraction of any particular constituent of the mixture. Now look at an illustration. We're trying to explain this ideal solution. We'll give an example. Of course, we have done this example in class. We try to solve that. So take your time. Just pause the video. Look at the calculation. Vapor pressure of benzene, that's the pure vapor pressure, is given. Vapor pressure of toluene, methyl benzene, is given. We calculate the molar mass. We know the formula is given here, 78, and for toluene, 92. Now, number of moles of benzene, gram given over molar mass, it gives us this. Number of moles of toluene, the gram given 4.6 over 92, it gives us this. Total number of moles is 0.15 plus this is 0.20. So we'll get the mole fraction for benzene and we'll also get the mole fraction to toluene. Here we're using B as benzene and T as toluene. And we made a note that for all ideal solutions, that summation of the mole fraction must be equal to 1. Now that illustration continues. The partial vapor pressure of benzene using Raoult's law, look at it. XB multiplied by this, we'll get it. Partial vapor pressure of toluene using Raoult's law again, we'll get this. So the total vapor pressure will be the summation of the partial pressure of the two. Remember I mentioned that Dalton's law. And when we add that, we'll get our answer. So it's possible for us to vary the mole fractions for the two constituents and now calculate the total pressures. And that gives us this graph here. For B, gives us for benzene, the variation for benzene, and T gives us the variation for toluene. And at any point when you add that for toluene and benzene, it gives us the total vapor pressure here. And for any solution that obeys Raoult's law, this is what you have, a straight line. So there are deviations from Raoult's law. Once there are deviations, this straight line A will no longer be there. It can be a concave, it can be a convex. That is, we're saying that this line will be a curve because of either positive or negative deviations from Raoult's law. We have discussed mixtures, solutions, and types of solutions. The way we can measure concentration of solutions. We have also looked at ideal solution and Raoult's law, and we use illustration to show vapor pressure of an ideal solution. Thank you very much for listening and hope to see you in the next class.